Have you ever wondered what makes lightning crackle across the sky, or how your smartphone charges wirelessly? The answer lies in a fascinating invisible process called ionization. It's happening all around us, silently shaping the world in ways we barely notice. Ionization is the unsung hero of countless natural phenomena and technological marvels. It's the driving force behind the northern lights, the reason salt dissolves in water, and the key to understanding the chemistry of life itself. In this exploration, we'll delve into the captivating world of ionization, uncovering its secrets and appreciating its profound impact on our lives. Get ready to have your mind charged with knowledge. Everything around us, from the air we breathe to the ground we walk on, is made up of tiny particles called atoms. These atoms are the fundamental building blocks of matter, forming the basis of all physical substances. Think of atoms like miniature solar systems with a central core and orbiting components. They have a central nucleus containing positively charged protons and neutral neutrons, which are tightly bound together. Buzzing around the nucleus are negatively charged electrons, which move in various energy levels or shells. Normally, atoms are electrically neutral, meaning they have an equal number of protons and electrons, balancing out their charges. But sometimes an atom can gain or lose electrons, altering its electrical balance. This process of electron transfer is what we call ionization, a fundamental concept in chemistry and physics. When an atom loses an electron, it becomes positively charged and is called a cation due to the surplus of protons. Conversely, when an atom gains an electron, it becomes negatively charged and is called an anion because of the extra electron. These charged atoms, or ions, are the key players in the drama of ionization, driving many chemical reactions and processes in nature. Ionization isn't a one-size-fits-all process. It involves various techniques and methods, each unique in its approach and application. There are different ways to coax electrons into jumping ship from their atoms. Each method has its own set of principles and conditions under which it operates. One method is through high-energy radiation like X-rays or ultraviolet light. These forms of radiation carry enough energy to disrupt the atomic structure. Imagine these rays as tiny bullets of energy, each one capable of causing significant changes at the atomic level. When they collide with an atom, they can knock an electron loose, creating an ion. This process is fundamental in many scientific and medical applications. Another method is through chemical reactions. These reactions can alter the electron configuration of atoms. Some atoms are more electronegative, meaning they have a stronger pull on electrons. This property is crucial in determining how atoms interact. When these atoms come into contact with atoms with weaker electron affinities, a tug-of-war ensues, and the more electronegative atom can snatch an electron away, leading to ionization. This is a common occurrence in many chemical processes. Heat can also induce ionization. The application of heat provides the necessary energy for ionization to occur. When you heat a substance, you are essentially giving its atoms more energy to move around. This increased energy can lead to more frequent and forceful collisions. If the temperature gets high enough, atoms can collide with such force that electrons are knocked off, creating ions. This method is often used in industrial processes and scientific research to study the properties of materials under extreme conditions. Ionization might seem like a hidden phenomenon, but its effects are anything but subtle. It plays a crucial role in various scientific and everyday processes that we often take for granted. Let's take a look at some real-life examples where ionization takes center stage, showcasing its importance and impact on our world. Lightning, that awe-inspiring display of nature's power, is a prime example of ionization in action. It's a phenomenon that has fascinated humans for centuries. During a thunderstorm, collisions between ice particles within the clouds create static electrical charges. These charges are the building blocks of the dramatic lightning we see. These charges build up, and when the electrical potential difference becomes large enough, it ionizes the air, creating a conductive pathway for a massive discharge of electricity. Lightning. This process is both powerful and mesmerizing. Ever wondered how a smoke detector saves lives? This small device is a perfect example of ionization at work in our daily lives. It uses ionization to detect smoke particles in the air, providing an early warning system that can be crucial in preventing disasters. Inside the detector, a small amount of radioactive material ionizes the air, creating a current between two electrodes. This current is essential for the detector's function. When smoke particles enter the detector, they interfere with the current flow, triggering the alarm. This simple yet effective mechanism can make the difference between life and death. Our own bodies rely on ionization for countless biological processes. It's a fundamental aspect of how our cells and systems operate. The transmission of nerve impulses, for example, depends on the movement of ions across cell membranes. This movement is critical for communication within our nervous system. Electrolytes, those essential minerals we get from sports drinks and food, are also examples of ions at work. They help to maintain fluid balance, muscle function, and overall health in our bodies, especially during physical activities.